So far in integration, we have discussed several different types of numerical integration techniques. We have discussed trapezoidal rule, we have discussed Simpson's 1/3 rule and Simpson's 3/8 rule. In this lecture, we'll see an interesting example of actually using this rule and get some integration done which we cannot do analytically. In particular, we'll get the value of pi using numerical integration here. So let us see how we proceed. The value of pi is of great interest for mathematicians since antiquity, and it was known for a long time that the ratio of area and radius square of a circle is a constant, and that is what is pi. People have tried to evaluate this value for hundreds of years, but here in this example we'll figure it out in few minutes, writing few lines of program. If we take a circle of radius 1, then the area of this circle will be pi, and that's what we are going to do here. We'll take a circle with its center at origin, its radius 1, just like this, and we know the equation of such circle will be x square plus y square equal 1. Now the area of this circle will be pi, but then the circle is symmetric, so it's not necessary to find the entire area. We can, for instance, remove half of it and find the area of this semicircle. And even here, we can remove 1/2 of this and find the area of this quarter circle. If I multiply this area with 4, then we get the area of the entire circle, that means the value of pi. So then the value of pi is 4 times this particular area, that is x going 0 here, because x equals 0 here, x goes 0 to 1, y dx. And what is y here? Y we can get as a function of x from this x square plus y square equals 1, and y is root over 1 minus x square. Here we are taking only the positive part of y, because we are looking only on the positive part of the geometry. Y negative will come down here, which we are not considering for our calculation. So now our goal is to evaluate this integral. Now in the beginning I said that you cannot do it analytically, but you know that you can evaluate this integral analytically. 0 to 1 root over 1 minus x squared dx, you can evaluate it analytically. But if you evaluate it analytically, this 0 to 1 root over 1 minus x squared dx 4 times, if you evaluate analytically, you will get the answer pi. You will not get the numerical value of pi. This is where it's very interesting. This is where the numerical calculation actually trumps the analytical solution. Even though for this integral we have the analytical solution, we still want to perform numerical calculation. So now what we'll do, we'll write a program to evaluate this integral, and you will see that it's very simple calculation. Few lines of program will do the job. My suggestion to you is that you stop the video now and you get ready for writing the program with your computers and compilers for whatever language you will be using in that. If you do not have any means to actually write program, or if you don't know how to write program, if you don't have time to write program, what you do, you at least with this lecture, you write the pseudocode for different methods for evaluating pi. So now get ready. We'll now go to the Jupyter notebook where I'll write the Python program for this problem. Here I have opened my Jupyter notebook and I have written here the problem in question. I've already written it out. So here we are interested in evaluating this integral a to b fx dx. A is 0, b is 1, fx is root over 1 minus x square. 3 expression for trapezoidal rule, Simpson's rule, 1/3 and 3/8. I have written it out because I don't want to go again and again and see the expression I am doing it right or not. So I have written them out. And now we will write program here. We will run it and see if it works. We know that value of pi will be about 3.14. So let's see what we get here. Okay, I am writing this program in Python. We are in Python 3 kernel. You can see it here. But you can write program in your own language. There is no problem. So let's start writing the program. Here I want to integrate this function. So first I give the interval a equals 0, b equals 1, and I have to take the number of intervals. So number of intervals, let us say 100. This is arbitrary number. And my h, I'm starting trapezoidal. So let us just denote here trapezoidal. Trapezoidal. And my h will be equal to b minus a by n So h is b minus a by n, and so to start trapezoidal I need to evaluate this y function. This y is my fx, and my fx is, let us just define f as a lambda function. So this will be lambda function of x, and to square it I need math. So let me import math. So this will be empty dot squared 1 minus x square. So I have defined my function root over 1 minus x square. A, b defined, h is calculated. So I'll start trapezoidal, and trapezoidal is that y0, yn, they are added up, and then rest will be twice. So now I initialize this trapezoidal. Let us say I name is a trap, and I initialize it with f of a plus f of b. These are my y0 and yn. So just keep on writing here that these are my y0 and yn. So this is a plus b. Now I have to loop and add others. So for I do not want to take the first term of y because first term I have already taken, last term will not come. So I'll give it 1 to n. Then it will take from 1 up to n minus 1, and that is what I need because 0 and n I have already taken care of. So I need this fx. So my x is equal to a plus I times h, and here I will give an increment toward my trapezoidal. So plus equal to the increment, that is 2 times f of x. Okay, so this plus equal to means strap equals strap plus 2 times f of x. So this gives the summation, and now I come out of this for loop. I don't need to be in the for loop. I did in the trapezoidal, I did whatever it is there in this within this bracket. So now what I do is that I take this out of this bracket and I write this strap is the strap multiplied by h by 2. So maybe I can write like this equals h by 2. So star equals means strap equals strap multiplied by h by 2. So this should be, this is 1/4 of this circle. So let us say that, let us print 4 times this strap. This is the program then. Okay, we don't need anything. We will print this and see that what happens. This should give us the value of pi. So let us run it. It is giving us 3.140, etc., etc. Okay. All right. So this is what I am getting. Now I want to try it with Simpson's 1/3. Okay. So let me put this trapezoidal box below so that I can see these expressions. So bring one above and I copy this trapezoidal. I'll take this and I'll edit over this. Okay, so this is going to be my Simpson 1/3. Okay, because this part will remain same. N is 100 here, and that this n is the number of intervals that should be even, and that is even here. So we are good about it. Simpson's 1/3. The difference between trapezoidal and Simpson's 1/3 is that here you have 4y1, here you had this 2, 2, 2, here you have 4. So some of them will be 2, some of them will be 4. So this is 0th, this is 1, 2. So if this is 1, so this is odd number, then this is multiplied by 4. This is y0, y1. When y is odd number, that is, then it is multiplied by 4. Rest are same, y0, yn, that would be same. So after this there will be no change. X, there is no change. So let me give it a different name. Simpson 1/3, and this is also Simpson 1/3. This is also Simpson 1/3, and here so Simpson 1/3. So now I have to do whatever I have to do here. So if I is odd, then it would be 4. Otherwise, it will be 2. So if I is even, then it would be 2. So let us put this way. So if I, the remainder of I, that means this I mod 2 is 0, then what we will do is that it will be incremented by 2 times fx. Yeah, so this is 2, this is fine. But if it is not, else what we will have is it would be 4 times. So let's copy it, and it should be 4 times. So that completes it, and then h by 3 here, h by 3. So hopefully this is all right. Let's run it. Okay, you can see this is 3.1411. So it looks good. Okay, so now we can go to Simpson's 3.8. I am adding it above it so that we can see this expression. Let us just copy this Simpson's 1/3. It should be something like this. So this is 3.8. Okay, rest of the things are like this, but n is 100 will not work. Here you have to take something multiple of 3. So maybe n90 we take. Then it is multiple of 3. So here this is Simpson 3.8. Here also 3.8. 3.8. We know that this would be 3h by 8, so we can do at least this one. Whatever the addition it is, that multiplied by 3h by 8. Okay, so what is the logic here? Logic here is that if it is this 0, 1, 2, 3, 1, 2, 3, 1, 2, 3, then 4, 5, 6. So you have 3, then 6, then 9, that would be multiplied by 2. Otherwise it will be multiplied by 3. First and last we are considering it here. So this is not 2. This should be equal to 3, right? If it is 3, it is multiplied by 2. Otherwise it is 3. Okay. So this should give us Simpson 3.8, right? Okay, let's see. Okay, you can see that 3.1409. So it's all of them are good. Which one is better? We don't know that. For that we have to take some higher number. So we can actually increase this number and see that, well, if it is like 900, then what happens? So 900, then 3.14157. So you can see that it is pretty close to a good number, but let's make everything 900. It will work for 900 because it works for even number. 900 is even number. 3.14157. So you can see that they are pretty similar. Simpson 3.8, Simpson 1/3, they are pretty similar because they are of same order of accuracy. More or less they are similar. So here I take 900 in trapezoidal. You can see 3.154. So it is also very close to Simpson and Simpson's 1/3 and Simpson 3.8. So this is how you can write programs here. These are very simple program, and you see that at the end you got the value of pi. If you want to calculate the centroid of this segment, quarter segment, then all you have to do is that you have to multiply with x before you integrate. So you have to multiply with x and then divide by the area. That should give you the centroid, which you can try. Okay. All right. So once again, you can see that this is a very simple exercise, and within a matter of few minutes, the program also takes fraction of a second to run. What you have evaluated, it took few hundred years for scientists, mathematicians to learn it. We are now doing it in fraction of a second. So that's the beauty of numerical method, which is in action here. So we are again here, and we have evaluated the integral that you have seen. It's a very simple process. Now we'll close this. So you have now seen that we have evaluated the value of pi, and we have evaluated it very easily. You have seen numerical methods in action. Now what you can do is that just slightly modifying this technique, you can get the coordinate of the centroid of this quarter circle. So if this is the quarter circle you have, and you have evaluated this y dx, this is your area, and if this is the centroid, let us say that this is xc, you can look at a mechanics book, you will find that it should be equal to x, this dA divided by a. And because of symmetry, the yc will also be same. So can you figure it out what will be the value of xc by slightly modifying this computer program that we have just discussed? If you cannot write the computer program, you write the pseudocode. You can also do some calculation manually to get this. So now you have some idea about how to implement the numerical integration in computer. In upcoming lecture, we will talk about slightly advanced technique. We will not do computer program for those techniques, but you will learn slightly advanced technique, and then we will move forward toward ordinary differential equation. That's all for this lecture. Thank you, and I'll see you in next class.